We are done with antiderivative techniques. There's no new antiderivative techniques that we need to learn. We do not have to learn antiderivatives of any other different types of functions. So the last two lessons of this unit are all about applying them and taking antiderivatives of different types of equations and different types of derivatives. And what we're going to focus on are what are called differential equations. And you've been asked to solve differential equations already. Back in Unit 7, when we introduced antiderivatives, it's like this is an application of an antiderivative. It is solving something like this, a differential equation. And in math, usually solving means like x equals a number. But in this situation, when you're solving a differential equation, you're actually taking an antiderivative to find an equation. Now, what we just come up with by taking the antiderivative of 2x plus 3 is what's called a general solution. A general solution has a plus c. But if you're given an initial condition, f of 1 is equal to 2, you can plug that point in to find c. And when you find c, it's not that c is the solution, it's that the equation with the found c is your particular solution. Okay, so my general solution has the plus c. My particular solution is still the equation with the c that is being found. Okay, let's do some tougher differential equations. Well, this is one type of tougher differential equation where U substitution is needed. And like as of today, you guys could do this one. You take the antiderivative of both sides, be no big deal. Actually, you just take the antiderivative. You don't know about the both sides part yet. And probably you wouldn't even write down the dx, but whatever. And you just say y equals, like, all right, well, u is equal to x squared, du is equal to 2x dx. I guess I have to go through a little bit of u substitution. I'll have the antiderivative of x e to the u 1 over 2x du. This is not new to us. It's just in a different form, and we'll have to find c. 1/2 e to the u, the antiderivative is 1/2 e to the u. So I'd have 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. But the one extra step today would be, for this type of situation, this type of antiderivative, to find c. Okay? Typically, we haven't had to find c. We just had to write it down. Now we're going to have to find it, plug in 2, plug in 0, find c. C would end up equaling 3/2. You get 4/2 minus 1/2. And we have our particular solution for this differential equation. Great. So this is one type of tougher differential equation. But we're not going to see many of those. We're going to go to different types of differential equations, like this guy. dy dx equals negative x over y. I don't like how that dy dx looks like. dy dx equals negative x over y. Now, what is different about this differential equation compared to other differential equations that we've seen? It's got two variables. It's got an x and a y. And it's like, how do I take the antiderivative of negative x over y? I don't know. I don't know how to do that. You guys don't know how to do that. And I don't even remember where this comes from. Okay? Like, where do you get a derivative with x's and y's? Actually, you should remember where this comes from. Because back in Unit 5, I asked you to find dy dx for an implicit equation like this. And do you remember taking the derivative of this implicit equation? I hope so. And what was the key to this? No, that wasn't the key. Yes, taking the derivative and understanding that the derivative of 4y cubed is not just 12y squared, but 12y squared dy dx. Subtracting then 6x and dividing by 12y squared, we'd end up with negative x over y squared. Well, guess what, gang? This is where we're starting, and this is where we're going. So we're going to be backwards implicit deriving. That should be a 2y squared. Thank you. I think I said it, but I didn't write it. Okay, pretty cool. Well, what do? How do I go backwards here? Before I tell you how to go backwards, we are going to analyze another way to kind of be able to understand what's going on. And understand our goal still is to find some y equals equation whose derivative is negative x over y. Okay, I want to find the equation, you know, whatever the shape may be, so that the slopes of the equation follow this pattern. Does that make sense, right? The dy dx are the slopes of the graph. I want to find the graph so that the slopes follow the pattern of the graph. Okay, good. Well, we are going to introduce something called a slope field. Okay, a slope field is a visual representation of dy dx. It is an aid to help you understand what your solution y equals will look like. So, this is what you do when you're asked to create a slope field. Sometimes slope fields will already be created for you. Sometimes you'll be asked to create a slope field. You're going to take an xy axis, and you're going to be given specific points. I'm going to give you all these points here at the zeros and the ones. So 1, 1, 0, 1, 1, 0, 1, negative 1, 0, negative 1, negative 1, negative 1, those points, okay? And what you are going to do is you are going to plug in your xy's into dy dx. And then you are going to graph a tangent slope. So, let's take this point 1, 1. Plugging that into dy dx would get negative 1 over 1, which is negative 1. I'm going to plot a very small tangent slope that's approximately negative 1. Cool? Let me do another one. 0, 1. I get negative 0 over 1, that's 0. So at this point 0, 1, I'm going to plot a very small tangent slope that's 0. Let's do one more, and then the others I'll just kind of fill in. Negative 1, 1. The slope will be opposite of negative 1 over 1, 1. And I get this. If I go to negative 1, 0, I'd have 1 over 0, which is undefined, so it'd be a vertical tangent slope. It'd be the same thing at 1, 0. If I go negative 1, negative 1, my slope would be negative 1. If I go 0, negative 1, I'd have a slope of 0. If I go 1, negative 1, slope would be positive 1. Okay? Now, what is this telling you? It's telling you, you know, if, just like we talked about, if we have some sort of graph, my tangent slopes need to, you know, follow that graph, right? So it's almost like what we're doing, hold on, I can do this. It's going to be great. It's almost like what we're doing is we're starting with just you, ungroup, we're starting with the slopes. And then from the slopes, it's like, oh, it's got to be something. My thing's not working very well today. It's got to have a shape like this. My solution must be some sort of parabola. Okay? Now, maybe you don't see it here, but if we continue to expand and plot more and more slopes, this is what we would see with negative x over y. Okay? Now, what would be our y equals graph? What would be our graph whose tangent slopes would follow this pattern? What shape? A circle. You could see that a circle would follow these tangent slopes. Now, this is just one circle. I could have a circle this big. I could have a circle even bigger. Okay? But it looks like a circle, an equation of a circle satisfies and will be our solution to dy dx equals negative x over y. It'll be the equation that we get. Now, who knows what the equation of a circle is? Just offhand. That would be the area of a circle. Good guess. No? Okay, that would be a circle of radius 1. X squared plus y squared plus some radius, equals some radius squared. This is the equation of a circle. You guys remember this from like pre-calculus? I think you did circles like this, okay? This is the equation of a circle. So I think that if I take the derivative of this, I'm going to get negative x over y. Turns out I do. But let's say we don't have time to create a slope field. We don't have time to visualize it. And let's say the slope field isn't so obvious and we can't really see that it's a circle. What are we going to do? Well, I'm going to show you how we can get to this solution, which we see is going to be the solution, another way. So let's go back to where we were. And this is the way you're going to do things. Slope fields are great and all, but they're more of like a tool and an aid. They're not super realistic when solving differential equations like this. Okay? You're not going to take the antiderivative right away. You're not going to do it. What you're going to do before you take the antiderivative is called separation of variables. You're going to separate your variables. Which means, algebraically, you need to get your x's with dx, and you need to get your y's with dy, algebraically. What do I mean by algebraically? Well, like multiplying both sides by y. That removes the y from this side and puts it on the left side with dy. Multiplying both sides by dx. That removes the dx from this side, puts it onto the other side, giving me y dy equals negative x dx. And guess what? When you've been solving differential equations, you've been doing this next step. You just didn't even know it. The next step is to take the antiderivative of both sides. And guess what? We only need 1 plus c. Why? It's like you take the antiderivative of a side. Shouldn't you have a plus c over here and over there? Brilliant, Mr. Jones. We don't know that they're the same. So you think if you have a c and a c and you subtract them, they go away. But it's not true. But they are both constants. And if you subtract one constant from another constant, you're just going to get a constant. So that's why I'm telling you, just start with 1. Okay, this is an important step. You only need 1 plus c. Okay, well, what else could I do? Let's get rid of the 2's. I can multiply everything by 2. And I get y squared equals negative x squared plus, should I write 2 times c? It's just another c, right? If I can subtract 2 c's and get a c, I can take a c and multiply it by anything, and it's still just c. A constant times 2 is just a constant. It'll be different than the previous c. However, it's still just a c. So this is another important thing to do. When we're manipulating c's, you actually don't have to change it. Okay, guess what? What did we say was our solution by looking at a slope field? A circle. What was the equation of a circle? X squared plus y squared equals r squared. I get x squared plus y squared equals c. What is that c? It can be anything depending on an initial condition. which means any size circle. C could be 100, C could be 10, C could be 16, C could be 20 million. Okay? Any size circle's derivative will follow dy dx equals negative x over y. Okay? So we got it. The slope field showed it. We just confirmed it using this process called separation of variables. All right? We're going to do more examples finding the general solution. We'll go back to slope fields, but really the whole slope field and the finding the solution, they are aids to each other, but you can almost treat them as like different lessons within this lesson. Okay? We're going to find the general solution for this one, starting by separating my variables. Algebraically, multiplying by y squared and multiplying by dx. Take the antiderivative of both sides. We only need 1 plus c. Okay, now the last example, I like solve for x squared plus y squared equals c, which is kind of like an implicit equation, which is great. You will be asked to typically put your solutions in y equals form, which means you need to solve for y. It's kind of a way for us teachers who are grading these things to make sure everything looks the same, because we can have any type of implicit equation looking crazily. But if I ask you to solve for y, it'll be a nice equation that we all will have. I'll multiply everything by 3. When I multiply c by 3, it doesn't change. And then I'll take both sides to the 1/3 power, or I'll cube root both sides. Now, it's important. I have to take the entire right side to the 1/3 power, which means the c goes in the parentheses. C's, if you're flipping both sides, if you're taking both sides to a power, you don't just leave it off to the side and say plus c. Okay? It does have to end up in, in the right spot. And this is my general solution. We're good. Now, I might ask you to find the particular solution with an initial condition. You can go. I'm going to keep talking. And all you would have to do is find c. 2 is equal to 3 times 1 plus c to the 1/3. Cube both sides. C is equal to 5. Fantastic. Y equals 3x cubed plus 5 to the 1/3. This is my particular solution. Next one. Okay, this one is a little bit different than the previous two in that it's not x over y, it's x times y. Algebraically, what would I have to do? I'd have to divide by y cubed, or multiply both sides by 1 over y cubed, giving me 1 over y cubed dy. Multiply both sides by dx gives me x dx. We'll have to take the antiderivative of both sides. Now the antiderivative of x, 1/2 x squared, that's easy. The antiderivative of 1 over y cubed, we will, especially after next lesson, forget to use the power rule for this. And a lot of people will tell me that this antiderivative is log absolute y cubed. That is not correct. It is correct if you write it as y to the negative third, and then you take the antiderivative using the antiderivative power rule. That'd be y to the negative second times negative 1/2. Now, they want y equals, so I need to solve for y. I'll have negative 1 over 2y squared equals 1/2 x squared plus c. I'm going to multiply both sides by negative 2. I'll have 1 over y squared equals negative x squared plus c. The negative 2 times the c is just a c. Now, in this situation where I have a ratio, you could kind of cross multiply if you wanted, but I prefer to just flip both sides. When you flip both sides, you get y squared equals 1 over negative x squared plus c. And then you can either take both sides to the 1/2 power, but I know you guys like to square root things. So we'll square root. Notice I put a plus or minus. Remember, when we have an unknown quantity squared, the original value y could have been a negative y or a positive y. We flip that over to this side to get the plus or minus root 1 over negative x squared plus c. Okay, so that is my general solution, and we'll just leave it at that. Let's do another one. This one is actually from an AP free response question, so it is definitely within your means of doing it. I would have to divide by y minus 1 squared, or multiply by 1 over y minus 1 squared, and then multiply by dx. Ready to take the antiderivative of both sides. Now, this is like a situation where we have, an ax plus b to the negative second. We can take the antiderivative of the outside and then make sure we multiply by 1 over a at the end. But since it's just y minus 1, there's no coefficient of y. I don't have to worry about it. I just have to almost take the antiderivative of stuff to the negative second. It ends up being the stuff to the negative first times negative 1. Leave the stuff. Undoing the chain rule. You could use substitution to get the same thing. I think it would just take too longer than it would need to take if you use substitution. Over here, same thing. You can take the antiderivative of the outside, since it's just a ax plus b inside of it, and then just make sure you multiply by the reciprocal of x, of the coefficient of x, and you get this. Now this doesn't look pretty, so we can rewrite. I have negative 1 over y minus 1 equals 1 over pi sine pi x plus c. Again, maybe let's get rid of this negative first. Does not have to write as minus c. Even if you multiply by a negative, it's still just plus a c, just c might be negative. Again, I'm going to flip both sides. Now, when I flip both sides, it's easy. Don't make it complicated. Just put everything under 1. And then I'm going to add 1. Again, don't make it complicated. Just take this big old thing and add 1. Notice when I flip, the c ends up underneath the fraction. Just like over here when I flipped, the c ended up underneath the fraction. We would manipulate c, put it in the right place. It's important. Okay? Now, the next two, I'm asking you to find a particular solution. So I'm given an initial condition. I'm asked to put it in terms of y equals f of x. Okay, let's see what happens. I got y dy after multiplying by y and multiplying by dx, 5x dx. Take the antiderivative of both sides. I get 1/2 y squared equals 5/2 x squared plus c. Okay, I'm going to want to solve for y, so I'm multiplying by 2. Then I'm taking the square root of both sides. Since I'm taking the square root, I need a plus or minus. Okay, there's a problem. The problem is they want the solution in terms of y equals f of x, which means they want a function. Which means if you plug in 1x, you get 1y. Okay, not like if you plug in 1 for x, you get 1 for y. If you plug in 1x, you get 1y. Well, if I plug in 1x, I get 2 y's. I get a positive and a negative y. Because of this plus or minus, this means we do not have a function. It's like you have a square root top and a square root bottom. Well, that can create like a circle or like a hyperbola, or if you think about specific square roots without an x squared, you could have a square root top and a square root bottom. These are non-functions. You have two outputs for given input. okay? However, they are telling you that y of 1 is equal to 2. So it's like if I have a circle, they're telling you y of 1, that's just equal to 2, not negative 2, as an example. Which means what they want is just half of your solution. In this case, the top half. What that means, and what we need to be careful of, is that since I just want the function, and since y of 1 is 2, I'm only going to want the positive side of this square root. So when I plug in 2 and 1, I'm going to get a positive root 5, 1 squared plus c. And I'm going to solve for c, square both sides, subtract 5, and I get c is equal to negative 1. Well, that means y equals, and just the positive, 5x squared minus 1. This means when I plug in 1, I'm only going to get positive 2, not plus or minus 2. It's just positive 2. Okay? This is the same one, same deal. Let me change it to 2y really quickly. Same deal. You'll see it ends up being the same thing. We'll have a square root. They want your answer in terms of a function, and now they're giving us that y of 1 is equal to negative 2. So it may be that we're looking at the negative side of things. Let's see. Separate your variables. Algebraically, be careful. For these, they're very similar, but if the y's are up top, just make sure you're dividing. Don't just move stuff. I'm multiplying by 2y on both sides. I'm multiplying by dx on both sides. Take the antiderivative. I get y squared equals 5 halves x squared plus c. Okay, and I square root, and I get y equals plus or minus root 5 halves x squared plus c. Okay. Now again, when I plug 1 in, I better just get negative 2, not plus or minus 2. So that means I'm picking the bottom half of things. So when I plug in negative 2, that'll be equal to the negative square root. We know that square roots are always going to give us positive values. But in this case, we'll need that positive value. We'll need to take the opposite of it. I'll square both sides. I get 4 is equal to 5 halves plus c. This is 8 halves minus 5 halves is 3 halves. And I'll have my function negative root 5 halves x squared plus 3 halves. Okay, this would be the particular solution we are looking for. Okay, so that's separating variables and simple kind of two-variable differential equations. Separate your variables using algebra. Take the antiderivative, make sure you include a plus c. Solve for y when you're asked to. Plug in your initial condition to find c when you're asked to, okay? We're going to finish up talking more about slope fields, these visual aids to differential equations. And some different types of questions you'll be asked for slope fields are first creating one. So I would go ahead and make sure you practice the AP free response problems. Where you need to create one like this. So make sure you know how to create one. Next thing you'd have to do is plot a potential solution. So they may give you a slope field. They may ask you to draw like one of these curves that fits the slopes. So like here is some dy dx out there, creates this slope field. And if we have the point 1, 1 as part of our solution, what would our solution look like? All you need to do when asked this, and it's very simple, is just kind of follow the tangent slopes and where they lead you, and what you are sketching is what's the potential solution, the y equals solution to whatever dy dx equals. Okay? So that's another thing. Same type of question to be asked in this way. Here is a slope field. What would be a potential solution? Well, if you kind of just like follow the slopes, you see it looks something like this. Well, what is that graph? Is that sine x, cos x, x squared, an x cubed, or log x? It looks like a cubic. Okay, that's something you should know. Okay, so that's another type of question. A different type of question. Match the slope field. Match the slope field with the differential equation. So this is a slope field. These are differential equations. Which one of these produces this slope field? Okay. Now my advice for you is to look at extremes. So any slopes that are zeros or undefined or verticals. So that means in this situation, all these points when x is 0, so like 0, 0, 0, 1, 0, 2, all these points, the slopes have to be undefined or 0 in the denominator, something like 1 over 0 situation. If I plug 0 in for x, so plugging in the point 0, 0, 0, 1, 0, 2, this would equal 1, this would equal 1, this would equal 0, this one would be undefined. So it's because of that process that I know dy dx equals 1 over x. And that's what I would go with. Here's another example. We have these slopes. Now you see the 0 slopes? It looks like it's on the y equals x axis. So 0, 0, 1, 1, 2, 2. The slopes would equal 0 for all those. So some of these have x's and y's, some of them just x's. But if I plug in these points, so sine of 0, that's 0. Okay, that works out. But then if I plug in 1, that would be the sine of 1. That's not 0. So that doesn't check out. So that's not it. I look at x minus 1, x minus y. Well, if I plug in 0, 0, 1, 1, and 2, 2, I'd get slopes of 0. So this one looks like it's good. Let's check this out. 2 minus 0, that's 2. So for this one, my slope at 0, 0 should be 2. That's out. Here, 0, 0, okay, that works. 1, 1, the slope should be 1 for this one, but no, the slope is 0. So this one's out. And that's how I get this one. Here's another one. This is a tricky one. And this is from an actual AP problem, AP test. Notice they all have x's and y's. And I'm going to look at some of the extremes. So here's a bunch of zeros. It's at y equals x and y equals negative x. I'm just going to pick like 2 points that I think will produce zeros. So like 3, 3 and negative 3, 3. I could try 3, negative 3, but let's see if I can reduce some from there. So if I plug in 3, 3, my slope should be 0. Let's see. 3, that's 9 minus 3, that's 9, so that's 0 over 3, so that's 0. So this one works. This is x squared minus y squared, well, that's 0 over 3, that also works. This works. Okay, here we go, x squared plus y squared. If I put 3 squared plus 3 squared, so that's 9 plus 9, that's 18, so this one's out. And then this is also an x squared plus y squared, so I'm not going to get 0 there. All right, now, what else could we look at? I have 3 possibilities. I see the slopes that are 1 and this slope that's negative 1. It looks like at the point 1, 0, the slope is 1. And then I see right here the point negative 1, 0. That slope is negative 1. Okay, so I'm going to try those and see, do I get 1 and negative 1? So let's see, I plug in 1 minus 0 over 1. So that's 1, so that checks out. If I plug in negative 1 minus 0, so negative 1 squared is 1 minus 0 over negative 1. Okay, this is interesting. Let's see. Negative 1 squared minus 0 over negative 1. So that's positive 1 over negative 1, so that works. Okay, so that's the slope of negative 1. So this one checks out for both of those. Let's see if the other ones do too. And if they do, then we're going to have to do even more analysis. So 1, 0. 1 squared minus 0 squared over 0. So I should have a vertical tangent slope if that's the case, but this slope should be 1. So that actually fails. So 1, 0 doesn't work. It doesn't give me a slope of 1. Let's try this one. 1 squared minus 0 squared, that gives me a slope of 1. Okay, so that checks out. If I do the -1, 0 point, I get 1 minus 0 because it's -1 squared. So that's a slope of 1, but the slope should be -1. So that fails, and it's through that kind of process of elimination that I'm going to pick A. One more. This one is just similar to creating a differential equation. dy dx equals x squared plus y squared. It creates which type of slope field? Well, I would just start plugging in points, you know? If you plug in 0, 0, your slope is 0. Okay, 0, 0, slope is 0. Yeah, that one works. That one works. This one works. I don't know if that works. Let's check another one. Let's try 1, 0. 1, 0, my slope should be 1. Okay, 1, 0 slopes 1. Nope, that's gone. 1, 0 slopes 1. Looks like it. 1, 0 slopes 1. That's a little steep, but we'll see. 1, 0 slopes 1. Looks a little steep as well. It looks like B could be my correct answer. Let's see. Where are some other differences? Here. Right here. You see this one, and this one, and this one. These two have slopes of 0 at the point, 0, 1. This one has a slope that's positive 1. So let's see. If I plug in 0, 1, my slope should be 1. Okay, slope of 1, that's a slope of 0, that's gone. That's a slope of 0, that's gone. That's why I'm selecting B. All right, those are slope fields. That's differential equations.